welcome to this fourth lecture in this series of lectures on numerical optimization. So far in the last two lectures, we saw some mathematical background needed for this course, and some of those concepts will be useful for understanding some of the theory that we are going to see today, especially the concepts on differential calculus and some analysis. Okay, so in today's lecture, we'll look at unconstrained optimization problems, how to solve those problems, what are the necessary and sufficient conditions for the solutions of those problems. So, to begin with, let us look at a constrained optimization problem, which is given here. So, you have a function f from the domain x to r, and x is a subset of Rn, and our aim is to minimize the function f where x belongs to the set x. So, this is a constrained optimization problem, but any unconstrained optimization problem is a special case of this constrained optimization problem, in the sense that if I replace this x by Rn, then it becomes a unconstrained optimization problem. So, our aim is to solve this problem, and for that we need the definition of a minimum. Okay. So, x star belonging to the set x is said to be a global minimum of f over x if the value of x star, the value of the function at x star is less than or equal to the value of the function at any other point in the set x. So, such a point x star is said to be a global minimum. For example, let us consider a problem where you have a function which on the left panel, which is shown in the black line, and let us assume that the constraint set is only this interval. Then you will see that the global minimum of this problem is it occurs at this x, and the corresponding minimum value of the objective function is shown here. Now, on the right panel you will see another function which is not as nice as the function on the left panel. So, you will see that there are lots of peaks and lots of valleys, and suppose we restrict ourselves to this interval, and assuming that the function goes to plus infinity beyond these points, although it is not of interest to us. We are only interested in this small interval, and you will see that in this interval, this is the point where the function achieves the least value, and the corresponding x star turns out to be this. So, among all possible points in the domain of that function on which we want to minimize the function, this is the point where the function achieves the least value. So, this is called a global minimum. Similarly, one can define what is called a global maximum. So, in the definition of global maximum, this inequality will be reversed. So, f of x star greater than or equal to f of x for all x belongs to x, for x star to be a global maximum. Now, in this course, many times I will be talking about minimization problems of this type, but the ideas that we discuss here can be easily extended by writing to the maximization problem, by writing a maximization problem as a minimization problem, which we saw how to do that was seen in the first lecture. Now, the question is that are there any conditions on f or on x or both, so that the function f does attain its maximum or minimum in the set x. So, can we have some conditions on this f as well as on x, so that the minimum or maximum is guaranteed in the set x. Now, for that let us look at some examples. So, let us take a function f x equal to x cube, where the domain of the function is a set of real numbers, and the function is defined from R to R. Okay. Now, the function is shown here in this plot. So, on the right side, the function goes to plus infinity as x goes to plus infinity, and on the left side the function goes to, when x goes to minus infinity, the function goes to minus infinity. Now, you will see that over the domain x equal to r, this function has neither a minimum nor a maximum, because the function extends to plus infinity and minus infinity. So, it has no minimum or no maximum. Now, in this case, if you look at the domain set, which is x, that is a closed set. The set of real numbers r, that is a closed set, but it is not a bounded set. So, that means naturally x is not a compact set. Now, do we want x to be bounded and not necessarily closed? We do not know as of now. Let us see another example. Now, here is an example where the domain x is a open interval a to b, and the function f is from x to r and defined as f of x equal to x. So, the function is shown in this figure, and so you will see that these endpoints are not included in the domain. So, that is why they are shown using some special symbols. Now, if you look at this domain is now bounded. So, unlike the previous case where the domain was not bounded, here the domain is bounded, but it is not closed. So, again x is not a compact set. Now, you will see that f attains neither a minimum nor a maximum on x, because f of a and f of b are not defined. So, we cannot have a minimum value of the function in this open interval a to b, but in this case you can get a bound on this minimum and maximum values, and those are called infimum and supremum. So, the infimum of this function is f of a, which is attained at x equal to a, and the supremum of this function is f of b, which is attained at b. But remember that a and b do not belong to the domain. So, we cannot say that minimum or maximum is attained, but in this case the infimum and supremum are possible. So, so far we have considered two examples where the domain x in one case was not bounded but closed, in the other case it was bounded but not closed. So, that essentially means that the domain was not a compact set. Now, so does that mean that do we need x to be compact to attain a minimum? Okay. So, let us look at one example. So, let us consider domain x to be the closed interval minus 1 to 1. Now, it is a closed set as well as a bounded set. So, hence it is a compact set, and let us define a function f from x to r as f of x equal to x if x is in the open interval minus 1 to 1 and 0 otherwise. So, in the open interval minus 1 to 1, the function is a straight line, and at the end points the function has a value 0. So, clearly you will see that the function is a discontinuous function on the set x. Now, again we can say that f does not attain a minimum or a maximum in this set x. So, remember that here x is a compact set and f is not continuous. So, compactness of x alone was not enough. Probably we need some more conditions on f, and that condition is the continuity of function f on x. So, suppose if we have x to be a compact set and f to be a continuous function on the set x, then can we say something? So, this leads us to the Weierstrass theorem, which states that if X which is a subset of Rn is a non-empty compact set and f is from X to R is a continuous function on X, then f does attain a maximum and a minimum on X. That is, there exists some x1 and some x2 belonging to X such that f of x is less than or equal to f of x1 for all x belongs to X and f of x greater than or equal to f of x2 for all x belongs to X. So this theorem was proposed by Weierstrass. We will not go into the proof of this theorem, but it gives us sufficient conditions for the existence of optima. That is, if f is a function defined from X to R, then we need X to be compact and f to be a continuous function on X. Then it is guaranteed that there exist 2 points x1 and x2 such that f of x1 greater than or equal to f of x greater than or equal to f of x2 for all x belongs to X. So, as I said that this Weierstrass theorem just provides us sufficient conditions for existence of optima, but it does not give you the necessary conditions for the existence of optima. For example, suppose we take a function f which is I have not written the explicit form of this function here, but assume that the function has a form like this. Now, the function is defined on a closed interval a to b. The closed interval a to b is a closed and bounded set and hence it is compact, but the function f is not continuous here. You will see that there is a break in the function at this point. Now, although f is not continuous, you will see that the function does attain a minimum at this point and the minimum value of this function is somewhere here. So, although f x is not continuous, f does attain a minimum in the closed interval a b for this case. So, this example illustrates that the conditions of Weierstrass theorem are not met, but the function does have a minimum, right. So, Weierstrass theorem does not talk about necessary conditions for existence of optima, it only talks about the sufficient conditions for optima. Now, here is another example. Let us define a function f x as x minus 2 square and it is defined from R to R. The function is shown here. Now, you will see that the function is continuous, but x is not compact. The set R of real numbers is not a compact set. So, again the conditions required by Weierstrass theorem are not met because x is not compact, but despite this fact the function does attain a minimum at this point and the corresponding x star is somewhere here. So, we will see. So, you will see that Weierstrass theorem just gives sufficient conditions for existence of optima or many optimum points, but does not give the necessary conditions for the existence of optima. But anyway, it is a useful theorem in the sense that if those conditions are met, like if f is a function from X to R and X is compact and f is continuous on X, then the minimum and the maximum are of the function f are guaranteed in the set X. So, now let us look at a general problem. So, you will see that on the left panel you will see that figure which we saw earlier in this lecture, that the function is very nice and attains minimum at a single point, and on the right panel you will see a function where there are lots of peaks and valleys, and if you look at this point for example, so in the neighborhood you will see that the function is increasing and the function has a least value in this if you consider a neighborhood around this point, but this value is still higher than the value which is called the global minimum. Right. Now, it turns out that finding this global minima is difficult. For example, it is very difficult to characterize or find the global minimum for a general nonlinear function. So, if you have a function which is nice as on the left panel, it is easy to find the global minimum, while on the right panel you will see a function whose global minimum is very difficult to find. And suppose we find this point which is the global minimum, then can we say that it is a global minimum? So, for that purpose we need to look at the value of the function at all the points and to ascertain that f of x star is less than or equal to f of x for all x belong to x, and that is going to be a very difficult task. So, identifying a global minimum or characterizing it is very difficult for a general nonlinear function. Only in some special cases one can characterize them very easily. We will see those cases sometime later in this course, but as of now we know that it is difficult to characterize this this global minima. So, it resulted in a concept of a local minimum. So, again let us consider x to be a subset of Rn and f to be a function from x to R, and let us consider a constrained optimization problem, and we are trying to minimize f of x subject to x belongs to x. Now, x star belongs to x is said to be a local minimum of f if there is a delta greater than 0 such that in the delta neighborhood of x star the value of the function is less than or equal to the value of the function at all points in the neighborhood. So, if you look at this point in the neighborhood, you will see that the value of the function is less than or equal to all the points. So, if you take a small neighborhood, remember that delta in the definition of local minimum can be very small. So, if you take a small neighborhood around this point and find out the function values at all the points, you will see that the value of the function is at least the value of all the value of the function at all the points in the neighborhood. So, similarly in this case it is true that the value of the function is at least the value of the function in the neighborhood, however small neighborhood that you take, and same is true in this case also. But here interestingly the function is almost flat in some range, and then in one direction it starts increasing and the other direction it starts decreasing. So, such points in which the function increases in one direction and decreases in the other direction, they are called the saddle points. So, and similarly in this case of course, this is a global minimum. So, it also is a local minimum because in the neighborhood the function value increases. So, from this definition one can extend this definition to the definition of local maximum. So, again as I said earlier that the inequality reverses in this definition. So, again one has to take a local neighborhood, it can be sufficiently small and find out the value of the function in the local neighborhood, and you will see that these points are local maxima. Okay. So, the definitions of local minimum and local maximum, they are centered around the neighborhood of a given point. Now, let us consider one example. So, here the function is shown here. Now, let us take a point x star. Now, x star by the definition of local minimum, that there exists a neighborhood around x star. So, that the value of the function is f of x is greater than or equal to f of x star. So, because of that definition there is a problem in this case. mainly that since we are allowing f of x star greater than or equal to f of x for all x in the neighborhood of x star. So, you will see that x star turns out to be a local minimum because of that definition. But by looking at the function, assuming that the function goes to minus infinity in both the directions when x goes to plus infinity and minus infinity. So, you will see that x star indeed is a global maximum. So, you have x star to be a local mean and as well as a global maximum. Now, to avoid such cases, one can think of a definition of a strict local minimum. Now, x star belonging to x is said to be a strict local minimum of f if f of x star is less than strictly less than f of x for all x in the neighborhood of x delta neighborhood of x star and x not equal to x star. So, you will see that then if we use this definition, then x star is a local mean, but not a strict local mean, and also it is a global max because the function value is highest at x star. Of course, at the other points at the other neighboring points also the function value is highest. So, remember that the global minimum or global maximum, they need not be unique. So, this is one example where you have multiple global maxima and x star is not a strict local mean. So, all these points which are in the neighborhood, they are not strict local minima. So, now let us look at the function again, this function we saw earlier. So, these are the points which are local minima, and not only local minima, they are strict local minima. Now, this is a point which is a weak local minimum. So, you will see that f of x star is less than or equal to f of x in the neighborhood of x star. So, such points are weak local minima, and this point is a global minimum. Now, earlier I said that this global minima are difficult to characterize. So, one may wonder that how about finding different local minima, strict local minima or weak local minima, collecting them together and then trying to find out the least among those. So, this idea may work in some cases, but may not work always. For example, suppose I have a function which is shown here and it goes to minus infinity. So, the domain of the function is the set of real numbers, and you will see that this x star is a local minimum. In fact, it is a strict local minimum because the value of the function in the neighborhood of x star does not reach f of x star at any point other than x star. So, it always exceeds f of x star. So, now if you look at this function and if you collect all the local minima, which is 1 in this case, that will not give you a global minimum because the function does not have a global minimum. The function goes to minus infinity in both positive x as well as the negative x direction. So, by collecting all local minima, it is not always guaranteed that we can find a global minimum of a function. So, one has to check whether the function has a proper form, so that collecting all local minima can give us a global minimum. So, now let us look at unconstrained optimization problems. As I said earlier that if we are trying to solve a problem from to minimize the function f from where x belongs to capital X, and f is a function from x to r and x is a subset of Rn. So, this is a general constrained optimization problem, and an unconstrained optimization problem is a special case of this. Now, to solve a constrained optimization problem, many times we need to solve an unconstrained optimization problem first. We will see those techniques later, but solving an unconstrained optimization problem is important to solve a constrained optimization problem. Now, to solve an unconstrained optimization problem, one has to solve many one-dimensional unconstrained optimization problems, which are of this type. So, in today's talk, we will focus on solving one-dimensional unconstrained optimization problems. They are very important to solve unconstrained multi-dimensional optimization problem, and these unconstrained multi-dimensional optimization problems are important to solve the general constrained optimization problem. So, this being an important problem, we will spend some time studying about the solutions of these types of problems. So, here is a unconstrained one-dimensional optimization problem where f is a function from R to R. So, remember that now we are not worried about the set X in this case. The domain of the function is the entire set of real numbers, the range is also the entire set of real numbers. Now, we want to solve this problem, and as we saw earlier that it is very difficult to identify the global minima of a function. So, we will restrict ourselves to local minima. Now, the ideas that we see here can be easily extended to finding local maxima also. So, the natural question that one would like to ask is that what are the necessary and sufficient conditions for a local minimum? Now, what do we mean by the necessary and sufficient conditions? So, necessary conditions are the conditions which are satisfied by every local minimum. For example, if suppose x star is a local minimum of this problem, then we can say that if x star is a local mean, then certain conditions are satisfied, and those conditions are called necessary conditions. And by sufficient conditions, we mean those conditions which guarantee a local minimum. For example, if at x star belong to R, certain conditions are satisfied, then we can say with guarantee that x star is a local minimum. Now, as we saw earlier that there might exist lot of local minima for a general nonlinear function. Then how do we characterize such local minima? That is the next question that we would like to answer, because again we do not want to find a local neighborhood along around x star and check whether the value of the function exceeds the value of the function at x star, because there could be infinitely many points again in the neighborhood, and we do not want to have any conditions which will require finding different points in the neighborhood and checking the function values. So, instead, is there any algebraic approach to check whether a particular point x star is a local minimum? Now, the ideas of differential calculus become very useful in this case. So, if the function is sufficiently smooth, that means it's a first order derivative, second order derivative and so on, they exist and they are continuous, then one can arrive at different conditions for characterization of local minima. So, we are going to see those conditions now. Now, let us consider a function from R to R and f belongs to C1. So, this C1 denotes the class of functions whose first derivatives are continuous. Okay, so, now we are restricting ourselves to functions whose first derivatives are continuous, and let us consider the problem to minimize f of x where x belongs to R. Now, here is the first set of conditions called first order necessary conditions. The result is very simple. If it says that if x star is a local minimum, then f dash x star is equal to 0. So, which means that the derivative of the function vanishes. So, if x star is a local minimum, the derivative of the function at x star vanishes. So, these conditions are called the first order necessary conditions. They are necessary conditions because if x star is a local minimum, of f, then these conditions are satisfied. So, that is why they are necessary conditions, and they use the first order derivative information. So, that is why we call them as first order necessary conditions. Now, let us look at the proof of this result. The proof is based on the fact that so we have a statement which is of the type A implies B. So, what we do is that we assume that B is not true and then say that A is not true. So, we saw this method of proof in one of our earlier lectures. So, let us assume that f dash x star is greater than 0. So, the result says that if x star is a local minimum, then f dash x star equal to 0. So, on the contrary, let us assume that f dash x star is greater than 0, and then we will prove that in such a case x star cannot be a local minimum. Okay. Now, since f belongs to C1, so its derivative is a continuous function. So, that means f dash belongs to C naught. Okay. So, let us take a interval d which is of size 2 delta around x star. So, x star minus delta to x star plus delta is a open interval. So, let this interval be chosen such that the derivative of the function at any point in this interval, the derivative of the function at any point in this interval is greater than 0. Now, that is possible, it is possible to get such an interval because we are assuming that f belongs to C1. So, at least in the neighborhood f dash is continuous, and we are assuming that f dash x star greater than 0. So, at least in the neighborhood f dash x is greater than 0. Now, if you write the truncated Taylor series expansion of f of x around x star and truncate it to the first order. So, what we get is the f of x is nothing but f of x star plus f dash x bar into x minus x star, where x bar is a point on the line segment joining x star and x. Now, remember that f dash x bar is greater than 0 because x bar is a point in the interval d. So, f dash x bar is greater than 0. Now, we are free to choose any x in the interval d. So, suppose we choose x to be in the open interval x star minus delta to x star. So, x minus x bar, x minus x star will become negative because x lies in this interval. So, x minus x star becomes negative. So, x minus x star becomes negative, f dash x bar is greater than 0. So, therefore, f of x will become less than f of x star, and that contradicts the fact that x star is a local minimum. Now, one can use similar ideas by assuming that f dash x star less than 0, and then the rest of the things follow as they are, except that you choose the point in the open interval x star to x star minus x star plus delta. So, in that case f dash x bar will be less than 0 and this quantity is greater than 0. So, their product will be less than 0 and therefore, f of x will be less than f of x star. So, in either case we come up with the contradiction that x star is not a local minimum. So, if x star is a local minimum, then the first derivative of the function should vanish. Now, here are some examples. So, on the left panel you will see a function f of x which is x minus 2 square, and the derivative of the function at 2 vanishes. So, you will see that the function has a 0 slope at x equal to 0, and then on either side the function is increasing. Now, on the right panel you will see one function which is f of x equal to minus x square, and at x equal to 0 you will see that the slope of the function is 0, but in this case x equal to 0 turns out to be a global maximum, and in this case it turns out to be a global minimum. assuming that the function extends to plus infinity here and function goes to minus infinity in this case. So, the slope of the function is 0 at a local minimum as well as at the local maximum. So, looking at the slope really does not tell us much about the minimum or maximum of a function at that point. Now, let us consider one more case. So, on the right panel you will see a function f of x equal to x cube. So, the f dash x at x equal to 0 is 0, but you will see that the function increases in one direction and decreases in the other direction. So, if you move x to minus infinity, the function goes to minus infinity. So, slope of the function really does not tell us anything about the existence of a local minimum or local maximum at that point. So, the points at which the slope of the function is 0, such points are called saddle points. Sometimes people also call it stationary points. So, the saddle points really do not give us any idea about the local minima or maxima. So, we need some extra information, and as I said that f dash x equal to 0 is just a necessary condition for a local minimum, but not a sufficient condition. So, if we collect all points for which f dash x star equal to 0, such points are called stationary points. Now, since we are interested in solving a problem of the type minimize f of x where x belongs to R, the natural question that we would like to ask is that how do we ensure that a stationary point is indeed a local minimum? And we have seen the case that checking the gradient of the function or checking the derivative of the function in the one dimensional case does not really guarantee a local minimum, right. So, let us look at the second order information. Now, on the left panel you will see the same function f of x equal to x minus 2 square. Now, the derivative of the function vanishes at this point. The second derivative of this function at x equal to 2 is 4, and that is greater than 0. Now, on the right panel you will see the function f of x equal to minus x square. The first derivative of the function at x equal to 0 is 0, and the second derivative of the function at x equal to 0 is minus 2. So, you will see that for this function the second derivative of the function at this point is positive, and for this function the second derivative of the function at this point is negative. So, the second derivative in some sense talks about the curvature of the function at that point. So, this function has a positive curvature at this point and this function has a negative curvature at this point. So, you will see that although the first derivatives of these two functions at these points are 0, it is the second derivative which tells us about the curvature, and that tells that this point indeed is a local minimum and this point indeed is a local maximum. So, let us look at the second order necessary conditions. Now, for the second order necessary conditions we need the second derivative of the function. So, let us assume that f belongs to C2, that is the second derivative of the function is continuous and the function is from R to R, and we are interested in solving an one dimensional unconstrained optimization problem. Now, here is a result about the second order necessary conditions. Now, if x star is a local minimum of f, then the first derivative at x star vanishes and the second derivative is non-negative. So, this result gives us the necessary conditions which use the second order information of the function. Now, how do we prove this? So, the proof is very easy. Now, by the first order necessary conditions we know that if x star is a local minimum, then f dash x star equal to 0. We already proved that result. Now, let us assume that the second derivative is less than 0 at x star, and then we will come up with the contradiction. Now, since f belongs to C2, the second derivative of the function is a continuous function. So, again as in the previous case, let us choose an interval around x star of size 2 delta. So, this is the interval D x star minus delta to x star plus delta. Now, since f2 dash is continuous, we can always choose this interval such that for any point in this interval D, the second derivative is less than 0, because we have assumed that f2 dash x star is less than 0. So, now let us write down the second order truncated Taylor series. So, f of x is nothing but f of x star plus f dash x into x minus x star plus half f2 dash x bar into x minus x star square, where x bar is a point on the line segment joining x star and x. Now, we know that from the first order necessary conditions that f dash x star equal to 0. Now, we also have chosen this interval such that f2 dash x is less than 0 for all x belongs to D, and x bar belongs to this interval. So, f2 dash x bar is also less than 0. Now, this quantity, this should be x star. So, this quantity is 0 and f2 dash x bar is less than 0, x minus x star square is greater than 0, x minus x star square is greater than 0. So, you will see that this quantity vanishes and this quantity is less than 0. So, which means that f of x is less than f of x star, and which is a contradiction. So, we will see that if x star is a local minimum, then f dash x star equal to 0 and f2 dash x star greater than or equal to 0. So, remember that this is f dash x star, and by first order necessary conditions f dash x star equal to 0. Now, the question is, are these second order sufficient conditions? Are these second order necessary conditions also sufficient? And the answer is no, because if you consider a problem which is to minimize x cube subject to x belongs to R, the function is drawn here. Now, at this point, the first derivative and the second derivative both are 0, but then x star turns out to be a saddle point. So, these conditions are necessary for the existence of a local minimum, but not sufficient. So, what are the sufficient conditions for the existence of a local minimum? So, let f be a function from R to R, f belongs to C2. The second order sufficient conditions result states that if x star is a point from the set R such that the first derivative of the function vanishes at that x star and the second derivative is greater than 0, then x star is a strict local minimum of f over R. So, remember that this is a result which guarantees strict local minimum of f over R. Now, the proof of this is again very easy, that since f belongs to C2, f2 dash is continuous. So, we will choose the interval D such that in that interval for any x in that interval f2 dash x is greater than 0, and that is possible because f2 dash x star is greater than 0. So, let us write down the truncated Taylor series expansion of f around x star. So, f of x is nothing but f of x star plus f dash x star into x minus x star plus half f2 dash x bar into x minus x star square, where x bar is a point on the line segment x star to x. Now, if f dash x star equal to 0, then fx minus f of x star is nothing but half f2 dash x bar into x minus x star square. Now, x bar is a point in the interval D. So, f2 dash x bar is greater than 0. This quantity is also greater than 0 because it is a square. So, the whole quantity is greater than 0. So, which means that f of x is greater than f of x star for all x belongs to D. So, at least in there exists some delta greater than 0 such that in the neighborhood delta neighborhood of x star, the value of the function does not attain f of x star. In fact, it exceeds f of x star. So, which implies that x star is a strict local minimum. So, remember that So, these sufficient conditions guarantee a strict local minimum of f over r. Now, are these conditions necessary? Do they though they guarantee that the local minimum is strict, they turn out to be not necessary conditions, because if we consider a case where f of x equal to x to the power 4, then x star equal to 0 is a strict local minimum, but then f dash x star and f2 dash x star are both 0. So, this second order sufficient conditions, they are not necessary in this case. So, now we have a important result which we will state without the proof. So, let us assume that f is a function from R to R and f belongs to C infinity, that is all the derivatives of the function exist and they are continuous. Let us also assume that f is not a constant function. So, let us rule out that possibility also, and let us denote the kth derivative of f at x as f k x and consider the problem to minimize f of x, x belongs to R. Now, here is the result which says that x star is a local minimum of f if and only if the first non-zero element of the sequence f k x is positive and occurs at even positive k. So, this is a very important result which says that if you start taking the derivatives of the function from the first derivative, second derivative and so on. Now, if you consider that sequence of derivatives of function f at x, so the first non-zero element of the sequence f k x star is positive and occurs at positive, even and positive k. So, that is very important. So, if you consider the example of f of x equal to x to the power 4, so you will see that if x star equal to 0 is a local minimum of that function, and the first three derivatives at x star are 0 and the fourth derivative is positive. So, the fourth derivative, that means that the k is equal to 4, which is a even and positive number, and fourth derivative of the function x to the power 4 is positive. So, that is why x star equal to 0 is the local minimum of f x equal to x to the power 4. Now, one can have a similar result for the local maximum. So, the only change that one has to make is that the sequence f k x star is negative. The first element of the first non-zero element of the sequence f k x star is negative and it occurs at even positive k. Now, let us see some examples to find out the minima or maxima, minima of a problem. Now, let us consider the problem minima is x square minus 1 square. Now, the first step to solve such problems is always to identify the stationary points, and the stationary points are found by equating the derivative to 0. So, if you take the first derivative of this function, and that turns out to be 4x into x square minus 1, and that equal to 0 implies that either x equal to 0 or x equal to plus 1 or x equal to minus 1. So, it has 3 stationary points. Now, we need to check which of these stationary points are local minima or local maxima. So, then we need to go for the second derivative information. Now, f2 dash 1 in this case turns out to be 8 and f2 dash minus 1 also turns out to be 8, and that is greater than 0. So, you will see that the first derivative is 0 at 1 and minus 1 and the second derivative is positive. So, the first non-zero element of the sequence f2 dash k of the sequence f k x star is positive and occurs at even k, which is 2 in this case. So, 1 and minus 1 are strict local minima, and along similar lines one can say that f2 dash 0, which is minus 4 and less than 0, implies that 0 is a strict local maximum, because the second derivative is negative, the first derivative is 0, and 2 is a even positive integer. So, 0 is a strict local maximum. Now, let us consider another case where minima is f of x, where f of x equal to x square minus 1 cube. Now, if you look at the stationary points, again we get 3 stationary points 0, 1 and minus 1, at which points the derivative of the function vanishes. So, we look at the second derivative. Now, second derivative information tells us that the second derivative of the function at 0 is 6, which is positive, which means that 0 is a strict local minimum. But at the stationary points 1 and minus 1, the second derivative also vanishes. So, we have to look for the higher order derivatives. So, let us look at the third derivative. Now, f3 dash x is a function like this, and you will see that f3 dash s, f3 dash 1 is positive, f3 dash minus 1 is negative. So, we really cannot conclude anything from our result about sufficient optimality conditions, because that these derivatives are non-zero at k which is odd. So, we can just conclude that 1 and minus 1 are saddle points of this problem, and 0 is a strict local minimum. Now, if you look at example x to the power 4, so you will see that f4 dash x is 24, which is positive, and all the earlier derivatives, right from the first, second and third, all these derivatives are 0. So, the first non-zero element of the sequence f k x star occurs at k which is even and positive, and the element is positive. So, which means that 0 is a strict local minimum. So, you will see that to solve such problems, we need to find the derivative of the function and identify the stationary points by equating the derivative to 0, and then go to the higher order derivatives from the second order derivative onwards to see whether we can conclude anything about the stationary points, whether they are local minima or local maxima. Now, if the problem is such a simple problem, then why do we need any algorithm to solve the problem? So, here is a simple example: minima is x minus 2 square, and f dash x equal to 0 implies x star equal to 2. So, 2 is a stationary point, and at that stationary point you will see that the f2 dash 2 is greater than 0, which implies that x star is a strict local minimum. So, as I said that if it is such a easy thing to solve f dash x equal to 0 and identify stationary points, then where is the need of an algorithm? So, here is an example. So, let us consider the example to minimize f of x equal to x square plus e to the power x, where f is a function from R to R. Now, the derivative of the function, which we will denote in this course mainly using the function g of x, that turns out to be 2x plus e to the power x. And if we equate it to 0, we really cannot find a solution of this problem in a straightforward way like what we did here. So, we need some algorithm to find out x which satisfies 2x plus e to the power x equal to 0, and that is where we will need a numerical procedure or algorithm to solve to find a stationary point of these kinds of functions. So, in general it is difficult to find the stationary points using a simple way like this, and one has to go for some algorithm to solve this. Now, there exist different kinds of algorithms to solve this problem. So, some algorithms they do use the derivative information, some algorithms do not use the derivative information, so but assume certain form of the function called unimodal function. So, we will see those things in the next class. So, in the next class, we will look at some algorithms to solve the problem of the type f dash x equal to 0 or finding the minimum of the function f of x without resorting to any derivative information. So, those are called the derivative free methods, and the methods which use derivatives, they are derivative based methods. So, we will see some of them to solve the problems of the type g of x equal to 0 or the problems where the derivative of the function vanishes or the function has the minimum. So, we will stop here and continue in the next class. Thank you.